Okay, so has the session started now? Good. So welcome everybody. This time I'm going to be taking the live session from my own office, so hopefully there should be no technical glitches. So let's get started. Again, my interest is to basically address the questions that you have and maybe talk a little bit about, some general topics. So let's go one by one. So there were some questions that were raised, and even last week they were raised, and I'm I tried to address them as best I could given last week's situation. So I thought I'll just go over it again a little bit, maybe a bit more carefully, and then a few other questions that people had raised. So let's get started. If you are able to, let me ask a favor of you. If everything is clear, if you're able to view this, just go to the chat, the live session chat, and just type saying everything. I'm able to follow what is going on. That will give us some feedback to let us know that this live session is going fine. Okay? If there is any issue, it's not reaching you, you're not able to access it, then if there's a glitch, then let us know. So we'll try to see what can be done to rectify the situation. Okay, so now let me share my screen so that we can start working with the boards. Let me just test it out. Yeah, that works perfectly. Good. So first things first. So last week there was a question on linearity of expectation. And the question was, can we have some intuition for the linearity of expectation? And without a device to write on and show something, it was a little bit difficult. But let me, so I thought I'll start by addressing this issue. So one nice thing I did was that I found, at least, is that there was an alternative proof of the linearity of expectation that may just be a little bit more intuitive. Okay? So this, by the way, I've taken it from the source I've given it over here. It's taken from OpenCourseWare from MIT. Okay? So you have two random variables, R1 and R2, and the linearity of expectation is just to show that the expectation of R1 plus R2 is the sum of their individual expectations. So this is classic linearity of expectation. And the question was why? Not just, I think the person who asked the question understood, go through the lines of the proof, but in some sense wanted to know why that is this even holds, and what is the intuition behind this linearity of expectation. So let's actually look at what is going on. Essentially, what is going on is that so let's notice one thing about this proof here. You're creating this new random variable t. That's the sum of R1 plus R2. Okay, so now you can think of the expectation of R1 plus R2, which was the left-hand side of what we wanted to of the equation that we wanted to prove. Okay. And so now, intuitively, what you're doing is you're combining R1 and R2, and look in this proof at least, you're looking at it as a single random variable. So now it's become the expectation of this random variable t. Okay. Now, if it is the random variable t, then each value that t can take So that's all these values S that T can take has certain probability associated with it. So you apply the formula for expectation. Okay. And so now you get the sum over all the individual values that T can take, and times the probability of those values. Okay, so you apply that. Okay. And now, so if you think about it, so suppose T takes the value S. S is really coming from two sources. There is an R1 associated with S and an R2 associated with S. The two added together was what led to this value S. So think of it as R1 of S, R2 of S. Okay, and so that's what they're doing. They're separating it out here. So the intuition here is the following. So this probability associated with that value S now can be taken into each one of these, can be associated, if you will, with each one of these random variables R1 and R2. So this is really the crux of why you can even apply, why linearity of expectation is true, regardless of what dependencies exist between R1 and R2. The probability associated with it can be somewhat separated out. So what happens now is this one big summation, because the probability can be taken in, can be separated into two summations. So there is that one summation here, and there is this other summation here. And you might be asking, so what is the intuition here at all? If there are some dependencies between these two random variables R1 and R2, why does it not matter? And so the best way to think about it is take an example and try to work it out for yourself. And we'll do that in just a minute. But the key thing to keep in mind is that the probability spreads into both R1 and R2. So in some sense, gets applied to R1 and R2 separately. And each of these boxes that I've drawn is essentially the formula for expectation of R1 and expectation of R2. And you get the linearity of expectation. Okay. So this is the formula. Let's look at an example. Okay. So let's take the case where R1 is equal to, let's say, +1 with probability equal to half, okay, -1 with probability equal to half. Okay, and now I'm going to create a random variable R2 to be completely dependent on R1. Okay. I'm going to say that R2 is -1 whenever R1 equal to +1, and +1 whenever R1 equal to -1. Okay, so what does this mean? R1 plus R2 will always be equal to 0. So if R1 is 1, R2 is going to be -1. So they're completely dependent on each other now, right? So now it's easy to see, right? So let's look at the expectation of R1 plus R2. Well, this R1 plus R2 is never going to be any value other than 0. So that's equal to 0. And similarly, the expectation of R1 is equal to also 0. That's coming straight from the fact that it's +1 will probably half and -1 will probably half. Now R2 is completely dependent on R1, but still the probability of R1 equal to +1 is a half, and R1 equal to -1 is equal to a half. So expectation of R2 equal to also 0. So you see this holds. Now let's flip things a little bit. So let's actually make a small modification just to see what happens. What I'm going to do, remember this R1 and R2 were what's called negatively correlated. One, when one of them is 1, the other one becomes a -1. So they kind of cancel each other out. What happens when they don't? When they kind of when they're positively correlated? So let's make this. So it's -1 when R1 is or rather, let me might be better. So would be to make this a +1 and this a -1. So basically. Sorry, I think yeah. So this, let me just correct that. Yeah. So now they're both going to take on the same value. So when R1 is +1, then R2 will also be +1. When R1 is -1, then R2 will also be -1. Okay. So they are now positively correlated. Now again, you can see that R1 plus R2 is in this case is going to be. Let's try to work it out. It's always going to be +2 or -2. Okay, and again, both the +2 and the -2 will happen with equal likelihood. So again, you have expectation of R1 plus R2 is 0. And these expectations, the individual expectations, don't change because the probabilities of +1 and -1 don't change. Okay, so you hopefully this example helped you sort of see that as long as the individual probabilities are whatever they are, however, whichever way they are correlated with each other, whether the two random variables are positively correlated, negatively correlated, or not at all, completely independent. So you can also think of R2 as being a completely different random variable with ±1 with equal probability. Then also this whole thing will hold, right? And it goes back to the fact that the probabilities, this probability of each combination kind of can be taken into this expression, and so then it leads to these each individual random variables, at least in summation, acting by themselves. Okay, in summation. So they could be dependent if you. So for example, if I know that R1 takes +1, I may know that R2 takes -1. But when you look at these boxes these red boxes that I've drawn, they are not based on individual values that one or the other takes. It's a summation over all possibilities, and so the dependencies get removed. Okay, so that's a long, unfortunately, a little bit of a long answer to a short question. So, but I hope that gives some intuition. Okay, so let me pause now and check with my TA to see whether there is any questions. Are there people? What's the? At least are there people logged in? Okay, good. So there are people logged in. So now let me take this moment to pause and remind you that if you have any specific questions, you have to type in the questions in the chat window, so that my TA Bharat can help out with reading out the question to me, and then I'll be able to hopefully address that. Okay, so now another question that got asked was the principle of deferred decisions. This is a small lag. Yes, that will be there. Okay. So one of the questions was, what is the mathematical basis for the principle of deferred decisions. Essentially, it is it goes back to the law of total probability. Okay, so let's look at the law of total probability. In this context, what we do is we take the universe. We have a universe, okay? And we partition the universe into disjoint events E1, E2, and so on. So E1, 2, E3, E4, E5, E6, and let's say E7. Okay. And now this is some partition, and then we are interested in some other event, let's say B. Okay, and the B takes some shape like this. Could be some shape. Okay. So what we are interested in is the probability of B. Okay. But the probability of B could be complicated, except when we condition on a particular EI. So let's say we are able to somehow get this probability easily, meaning we are able to get the probability of B conditioned on E2. And we're also able to get that not only for E2, we're also able to get that for probability of B conditioned on E1, and so on up to probability of B conditioned on E7. Okay. So somehow we have all of these probabilities. If we're able to, if you think about it, it often happens that when you condition on some E2, that means you've broken down the problem and focused on a very limited setting where E2 has occurred. So that's the intuition here. So if you have these probabilities, and you also have the individual probabilities of these events, then you are able to compute probability of P, because that's just equal to this plus, and so on. You just add up all of these probabilities. Then you will get the probability of P. What has happened? So let's look at one specific box. I mean, one specific term here. So that's this term. That is nothing but probability of B given E2. Okay. Just a second. So now there are these individual terms here, right? So now let's look at this one box here. So that essentially captures this part of the probability. Okay. So each of these summations. So for example, the very first one will actually be 0 because there is no intersection between E1 and B. Okay. So that will be 0 in this particular case. But each term basically captures its own portion of B. Okay? So I think the law of total probability itself is fairly clear, but I just wanted to remind you of that. Because now let's go with this reminder of the law of total probability. Let's go back to the principle of deferred decisions. Okay. So what happens now is that there are several variables, several let's say, let's actually create an example, a simple example. Let's suppose that we have some n coin tosses, and we want to argue that the probability that the number of means the number of heads is odd. So let's assume that so we want to be able to prove this. We want to argue that the probability that the number of heads is odd is exactly a half. Okay, so we don't know n. Let's say, for example, n equal to 3. Then you can have various options, right? T T T T T H T H T T H H and so on. Okay, up to H. And you want to argue that the number of heads is odd. So one thing you could do is you can work through all the 2 power n options, right? And there could be other ways to do it. But let's try to use the principle of deferred decisions. Okay. So here, what are we doing? We have n variables, n events, basically the outcomes of n coin tosses. Some of them we're going to artificially set, okay, and then focus on some alone. And specifically in this context, what we're going to do is let's say that C1, C2, and so on up to Cn are the n coin tosses. So okay, are the n coin tosses. So what we're going to do is we are going to assume that these first n-1 coin tosses are already done. Okay? And then we're going to focus our attention on Cn. Okay? Now, how does this relate to the law of total probability? Okay? So what are we doing when we set C1 through Cn-1? What we're doing is we are taking the universe and we are breaking it into, or partitioning into 2 raised to the n-1 parts. Okay? So let's look at one such part. Okay? What is that one such part going to look like? It is going to be the assignment of value C1 to Cn-1 as some specific sequence. So it could be specifically say H, T, T, H, H, blah, 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 up to something. This is n-1 outcomes, coin toss outcomes. Okay, so now if you consider all such possible n-1 outcomes, you basically partition the universe into 2 to the n-1 parts. Okay, now what we need to so essentially what I'm going to do is just going to draw all such parts. So I'm not going to draw it like it's a partition. You have to assume that it's a partition. Okay, I'm just, for simplicity, I'm going to draw it in some sort of a ring-like fashion. Okay. Now what I'm going to do is draw another event, which is the probability that the number of heads is odd. Okay. So now let's focus on this. Okay. How is the claim is this, that this shaded portion is going to be a half. Okay. Why is that the case? And that's easy to see, because what we have done is, when we are focusing on this event, this we have specified the first n-1 outcomes. We have specified the first n-1 outcomes, and but whether the final number of heads is even or odd is therefore dependent only on this last coin toss outcome. This is the one that we have deferred. The rest we have fixed. So when we are focusing on this one outcome, we have fixed the first n-1, and the very last one we have not focused on. But that is the one deciding event that decides whether the final total number of heads is odd or even. So let's now think about okay. So let me isolate that portion. So basically what we've done, this is, let's say, this particular event. So let me call that some EI. I'm going to draw that EI here. Okay. So what is the what is the probability given EI? What is the probability that it's going to be odd, or the total number of heads is going to be odd or even? Well, that will depend on two things. Okay, what is the number of heads in first n-1 tosses, and then the second thing it will depend on is the the last toss heads. Okay. So these are the two things that will matter. But because I have fixed EI, this is already fixed. This is already fixed. We don't the number of remember we have fixed this portion. This is the portion that is already fixed. So we have already, that it means that we are conditioning on this EI. So this portion is already fixed. Okay, but regardless of what that is, this portion is the last toss, heads or tails, is going to be it's going to hold with probability half. Okay, but regardless of the previous number of so let's take an example. So let's say that this EI here, the number of heads was 52. Okay, then the last coin toss is what is going to dictate what is going to happen, because now with probability half, the last coin toss is going to be heads, in which case the total number of coin toss is going to be 53, and therefore it's going to be odd, the total number of heads, or it's going to be a tails with probability half, in which case it will remain 52. Okay? And you can work it out regardless of what this was. The final outcome of odd versus even is going to be a half, based on whether the last coin toss was a heads or a tails. Going back to this picture, what is the intuition here? So because we when we fix these, essentially what we're doing is we're fixing on one of these partitions. There are we're taking the universe and we're just partitioning it into little pieces, and then we're focusing on that one piece. Because we are conditioning on this portion, it allows us to forget about this part and then focus our attention just on this very last coin toss, right? So that is essentially what is happening. We're able to take this huge probability space, condition on one portion of it, okay, and then focus on proving whatever we want to prove. Okay, so that is essentially what is happening over here. And when we do this carefully, we are able to prove exactly what we want to. Okay, so this is this I hope addresses the the mathematical basis. So let me just check with my TA if there's any question.
In an experiment of tossing a coin repeatedly till exactly 2 consecutive hits, find the expected number of times till this happens. Assume that probability of hit is P. And please generalize this to n consecutive hits instead of 2. There's also a comment here. I looked at the solution on Google, and expected value of x is being calculated similar to that of geometric random variable. What I don't understand is that even though it is intuitive to see that x has a memoryless property, where x is the random variable denoting the number of tosses required to get n consecutive hits, I would like to, can we mathematically prove that probability of x is equal to I plus k, given probability of x greater than I is probability of x equal to k. That is the memorylessness.
Okay, so
3 parts to the question. First part, probability of head outcome of a coin toss being heads is P. Given this information, what is the expected number of tosses I need before I see 2 consecutive hits?
Okay.
Now generalize this to n consecutive hits.
Okay.
And is this x which measures the number of tosses a geometric random variable?
Okay. I have to think a little bit about this carefully. So let me start with the simplest form of the question. Okay, so the simplest form of the question is you have a coin, and let's even start with p equal to a half. Okay, and the question is, and you also have a k value, k equal to 2 to begin with. Okay, so the question is, I want I define a random variable x to be the number of tosses until k, in this case, equal to 2 consecutive hits. Okay, and we want to understand the expectation of x. So this is the simplest form of the question. Okay, so now let's think about this. I haven't thought about this question, or at least don't remember having thought about this. So we have to work through this a little bit carefully. But we can apply the. Give me a second.
Probable strategy to solve this. So basically, you write a recursive equation expected value of x. Then,
but can we use linearity of expectation somehow? No, probably
example,
not. Right?
For example, let's say that I toss 1 coin. It's not heads. Then I need expected number more to see.
Okay, all right. So yeah, so let's try to think about. So Bharat here had an idea that might be something that will work. So let me think about this for a second. So now I think about this first. It is. What does it mean for x equal to, well, x cannot be 1, x will have to be 2 or more. Okay, so I'm just thinking out loud here, 3 and so on. So, which means that the outcomes are, let's see, k consecutive hits. So now, okay, so what you're allowed is multiple tails, heads, tails, and so on. But when you have two heads, that's when you stop. Okay, so you cannot use linearity. I think we need. I think we really need to formulate our answer before we can do that. So my apologies, but I don't think I'll be able to give a very quick answer because I have not thought about the specific question, and would be better if the TA and I had a chance to discuss. We also have had a chance to figure out how exactly to communicate the answer. So it might be better if we defer this question either a little bit later today itself. It's already about 5:40, so possibly not today. But certainly, one thing we can do is we can send out an email or an announcement with a better answer. But I don't think we should try to answer it at this point in time. What I'll do is I'll try to instead answer the other questions that came up. There was one more specific question. Assignment 4 question was there, right? Yeah, so assignment 4, one of the questions that was asked was problem number, this assignment 4. Yeah, so problem number 5 in assignment 4. I think that would be something I can answer in the time frame that we have. So here we are given a coin with bias 1/3, okay, and xi equal to 1 if the ith flip of that coin is heads, 0 otherwise. Okay. And of course, we toss this n times. So capital X is the total number of heads. So that's given by summation I equal to 1 to n xi. Okay, and which implies that the expectation of x is equal to, using linearity of expectation, it's the sum of the individual expectations, and that's nothing but n over 3. Okay, I think this part is easy. Now let's look at what the question is asking. Okay, just one thing to keep in mind is this n, the number of coin flips is equal to n, and this is an unknown. In fact, this is what we want to solve. We want to ensure. So let me read the question. At least that part of the question. We want to find determine the smallest value of n, so that the probability that at least half the coin flips come out heads is less than 0.001. Okay? So in other words, you expect to see n over 3 heads. Okay? If n is small, so let's say, for example, n is, let's take an example, n equal to 3. Okay? In which case you will expect to see 1/3 of the coin flips to come up heads. But now, what is the probability of getting 2 heads out of those 3 coin tosses? Well, that's going to be n choose n choose 2. So basically, you choose 2 of them. Time 1/3 for those 2 coin flips, and then 2/3 you can have the tails coming up. Okay, so if you work this out, so here in this case n is 3. So if it works out to something like, if my math is not completely way off, it's going to be something like 1/3 raised to the 4 times 2. Okay, and sorry, so this is not sorry, this is going to be 3 times 1/3 squared times 2/3. So that's going to be 2/9. Okay, if my math is not gone wrong somewhere. So this is a significant probability. Okay, so when n equal to 3, obviously this is not working. So what we want is the probability of having more than n/2 number of heads. We want that probability to be less than 0.001. Okay, and we can achieve this by increasing the number of coin tosses. Okay, by suitably increasing the number of coin tosses. And in fact, if you look at all the answers given, it's 198, 249, 307, 349. So we basically want to show that give the number here such that if you toss that many times, the number of heads exceeding n/2 will now become very, very small, say 0.0, something less than 0.001. Okay, but in this question, we are also specifying what approach to take in order to solve this problem, and we particularly want you to apply Chernoff bounds. Okay, that specific Chernoff bound that is given over there. Okay, so for that Chernoff bound, we already have. We require a few things. We require mu, so we'll require mu. Mu is n/3. We will also require delta. Okay, and if we have these two, then we'll be able to compute the appropriate value of n. So let's see how that works out. Okay, so now what we want to ask is the probability that x is probability that x is greater than n/2. This probability, we want that to be less than or equal to 0.0. In fact, strictly less than 0.001. Okay, so let's focus on this. Probability that x is greater than n/2 can be, we want that to be written, now we want to apply a Chernoff bound, so we want that to be written in the form x is greater than or equal to 1 plus delta times delta times mu. Mu is n/3, so I'm just going to write that as n/3. Okay, so this means that I need to compute the appropriate value of delta. So let me do that on the side here. 1 plus delta times n/3 should be equal to n/2. So solving that, basically I think 1 plus delta will be equal to 3/2, which implies that delta equal to 1/2. Okay, so now we even have the value of delta. Okay, so this probability, so that's equal to the, write it out, x greater than or equal to 1 plus 1/2, which we know by applying this formula is e to the minus mu is n/3, delta is 1/2, so 1/2 squared is 1/4. 4 times 1 over 3. And we want this whole thing to be less than, and remember this is, we want this whole thing to be less than 0.01. Okay, and that's 0.001. Okay, and that's now we just have this inequality, and we just have to solve for n. And this part I think you can possibly do it. So now if we take the ln, well, maybe first we should do is remove the negation from the top, so it becomes e to the n over what is this going to be? 30, is it 36? Yeah, 36 is greater than 1000. Okay, and now I can take the ln on both sides. So it's going to be n by 36 is greater than ln 1000. Okay, and so the 36 can go over here. So what we want is the smallest value of n such that this inequality holds. Okay, and that you can just punch it into a calculator, and will come out to something like 248 point something. So the integer value that will satisfy this condition is 249, which is the answer. Okay, so that addresses all the specific questions that people had raised in the Google Drive sheet. So in the Google Forms. Now might be a good time. So it's about 10 more minutes to the closing time today. So I don't know if we will have time to answer any more technical issues, but maybe I should address the final exam. Okay. So the final exam is going to be out of 50 marks. So there's going to be 50 questions, and the pattern is going to be basically a lot of multiple selection problems. And one thing to keep in mind is that a lot of the problems will have multiple correct choices. So what does that mean? It will, if there are 4 choices, it's not, you might have been used to multiple choice questions, in which case exactly 1 out of the 4 questions is correct. But what we have is multiple selection questions, meaning it might well be an example of this is which of the following. So let me try to think of an example. An example might be which of the following statements are true. Okay, and one of the statements could be given to random variables. The expectation of the sum of those 2 random variables is the sum of their individual expectations. And the second option, let's say, is something like what is the variance of 2 random variables? Variance of the sum of 2 random variables is always equal to the sum of their individual variances. Okay? And maybe the third one could be another statement. So the first one, let's say, first one was essentially, if you just for you to recall, was the linearity of expectation. The second one, the claim was the variance of x1 plus x2 equal to variance of x1 plus the variance of x2. And let's say the third one was something like let me just to illustrate the point, the probability of heads in 3 coin tosses is with three, let's say 3 unbiased coin tosses is 1/8. And then the fourth one is the probability of heads, tails, tails, heads in 4 coin tosses is 1/15. So let's say these are the 4 selections available. Obviously, this is true. This is true. This is not true. And here, because I've not specified that x1 and x2 are independent, this one also is not true. So you notice that there can be multiple correct answers, and so all the correct answers will have to be chosen. So I just want to emphasize that you have to read through all the choices and then make your selection. Okay. So this some of the assignment questions had this feature, but not all of them. In the exam, we have more of these, so you need to be watchful for that. The second thing I want to point out is that there will be comprehension questions. So there will be portions of the textbook, either our textbook or some other textbook, where and you'll be asked questions based on that portion of the textbook. So you'll have to comprehend it. And sometimes the questions will be slightly straying from that, in the sense that not only exactly questions based on that text, but just to understand the text, you may need some prerequisite information. So questions of that nature. So you need to be able to read some material quickly, digest it, and try to answer the questions. So that is another aspect of the final exam that I want to point out to you. Okay. So and then there will be several questions straight from the assignment. Okay. So if at all there may be some minor modifications. So I certainly don't. You should not mug up and come in and try to answer the assignment questions. I think a certain percentage, about 20% of the questions, or maybe even more, or maybe like 30% of the questions will be straight from the assignments. But you will need to still read and carefully understand the question, because there might be some very minor changes that are there in the final exam. Okay. So that's about all I had to say for the final exam. So let me, yeah.
Are there subjective questions?
What does that mean? When you say subjective questions?
Maybe like some where they have to enter the answer.
No, there are no subjective questions. They're all going to be multiple selection questions. So there is there won't be any requirement for you to enter a number or write a sentence or anything like that. It's all going to be selecting answers. But keep in mind that it's not just one correct answer that you may have to select. You may have to select all the correct answers. Okay. So that's that. Are there any other questions coming from the audience? Okay, so there is okay. So what we will do, we in the next few weeks until the final exam, we will still be monitoring the Discord server. I think Bharat, the TA Bharat, will be monitoring that. And also, if you have any specific questions, you can also yeah. So basically, that would probably be the right place to raise any questions that you have. If you feel that there is some topic that I need to teach again, and you raise it up, we may even be able to have a few more live sessions. But you will have to tell me in advance what topic you want me to cover. Okay, so I will come prepared for those topics alone, and I'll try to address those questions. So take advantage of that. You ask your questions. Prepare well. Any doubts, just make sure you raise it up, okay? And then we'll try to address it the best we can. So there is still one pending question that will require a little bit of time for me to formulate the answer and post it. So I will probably post it. I'll send it to Bharat, and Bharat will post it in the Discord server. So hopefully you should be able to get the answer from there. Okay. Any final questions, concerns, issues before we wind up? Good. So thank you very much for all those who patiently listened through this session. So let me just go back to. I think now. Yeah. So thank you very much. I appreciate your patience. And with this, I'll stop the broadcast for today. And any questions, just raise it up in the Discord. And if you want me to go over some topic again, tell me. Send an email. I mean, post it in Discord requesting for that. And we'll try to accommodate that. Okay. Thank you very much.